Hello everyone. Let's try to go through the questions, the answers for Carbonyl quiz. We look at the first question. This compound is CPA, is a drug. Which of the following statements about CPA are correct? You say 1 mole of CPA undergoes condensation with 3 moles of 2,4-DNPH. What it means, it must have 3 carbonyl groups, right? Okay, but there's actually only 1 and 2 carbonyl groups. Okay, this is actually an ester, so it's actually not considered. So this is actually wrong, is because it's supposed to be 2. Okay, let's look at question number 2. Option number 2. 2 moles of yellow PPT is formed when 1 mole of CP is formed with alkyne equals iodine. In fact, if you look at this, there's how many structures will give you either form test. There's actually only one structure that can give you either form test, which is this, right? So the answer is not 2, but it's supposed to be only 1 mole of yellow PPT, because you have only 1 mole of only one of the methyl ketone groups, right? So let's look at option 3. CPA does not cause a color change in hot acidified potassium dichromate. Okay, so is there anything here that can be oxidized? All right, alkene cannot be oxidized by dichromate. This is a ketone. Ketone cannot be oxidized here. This is also ketone. It shouldn't be oxidized, all right? Okay, but I would say one thing about this one. If you notice, all right, there's actually an ester here. Okay, the ester can actually undergo hydrolysis. Okay, the ester can actually undergo hydrolysis, which means it can actually break here. But when it breaks there, what you end up getting is an alcohol here and a carboxylic acid, right? But this alcohol is a tertiary alcohol. So actually it can undergo hydrolysis because of the acid and the heat. But because this is a tertiary alcohol, it cannot be oxidized. So there will not be a color change, right? There will be a color change. All right, so this is a statement is correct. So the answer is D. Okay, let's look at next question. All right, what are the types of reaction in this reaction scheme? Okay, so if you remembered what I taught you under Grignard reagent, I mentioned that this bond will break, all right, and then you get the nucleophile. The nucleophile is the C2H5, and this is the nucleophile. So you have the carbonyl. Maybe I'm just going to draw the carbonyl over here. So this is my carbonyl, all right? And we know that the mechanism works this way. Okay, this nucleophile attacks this carbon, electrons goes to the O, all right? So you end up getting this. So CH3, CO minus, H3, CH2, CH3, all right? Okay, so after that, of course, when this part breaks, you get MgBr plus. Okay, so in fact here you get MgBr plus. All right, so this is what you get. All right, so this is your nucleophile. All right, so which means this reaction is nucleophilic addition. It's reacting with carbonyl. All right, okay, let's look at the next part. How do you get this reaction here? You notice what they did. They actually plus water. All right, and actually water broke up into H plus and OH minus. So the H plus actually goes to the O minus here. So you notice you get OH. All right, OH. You see that? And then the OH minus here combined with the MgBr plus. Okay, so this is what you get, MgBrOH. So this reaction actually is better to put hydrolysis, right? Hydrolysis, because it involves the breaking of the water. It's reacting water and it's breaking of the OH bond, right? So hydrolysis is definitely a better answer than acid base. So the answer is D. All right, the answer is D for this. Okay, let's look at the next question. Okay, question number 3. Okay, question number 3. The following compounds are responsible for the smell. Which of the compounds can be oxidized by potassium dichromate? Okay, this is aldehyde. Okay, this part is aldehyde. Let's look at all the different groups. This is a primary alcohol. All right, this is an aldehyde. This phenol, right over here, and this is actually an ether, but it's for A level we take it as unreactive. Okay, a lot of alkenes over here, right? There's a lot of alkenes. Alright, and this actually is a ketone. It's a ketone over here. Alright. Okay, so which of the compounds can be oxidized by potassium dichromate? Okay, so dichromate can probably oxidize primary alcohol and aldehyde. Right? So the answer so what can potassium dichromate? Which of the following compounds can be oxidized by acidic dichromate and can be reduced by sodium boron hydride? Okay, so potassium dichromate, right? Potassium dichromate probably can oxidize. Let me see here. So what can it oxidize? It can oxidize alcohols, but only primary and secondary alcohol. Both it can be oxidized. It can also oxidize aldehyde. Okay, so take note. Of course, cannot oxidize ketone. So sodium boron hydride can reduce aldehyde, and it also can reduce ketone. Alright. So which means which of the compounds can be oxidized by potassium dichromate and can be reduced by sodium boron hydride? So if you look at this, one is correct. Okay, you can have an aldehyde. And secondly, okay, so you must see what's common between them. Okay, let's see what's common between them. So what's common between them is actually an aldehyde here, right? What's common between them is actually aldehyde here. So you must make sure your compound has an aldehyde. So I guess the answer is only 1 and 3, right? Okay, so let's see, the option is B. Okay, let's look at the next question. Okay, question number 4. Okay, let's look at question number 4. Alright, enantiomeric excess is a measure of the excess of one enantiomer. If R enantiomer makes up 75% while S enantiomer makes up 25%, we say there's excess of 50. So it's actually 75% minus 25%. Okay, which of the following reaction will result in a mixture which gives a excess of 0%? So to get 0% means you must have both 50%. So 50% minus 50% give you 0%. So what I try and tell you is it's something like a racemic mixture, right? 50% of each. Okay, so which of the these they must be enantiomers. Alright, okay, so let's look at this mechanism. Option 1. This is a secondary alkyl halide. So secondary alkyl halide can undergo SN1 or SN2. Alright, so in fact some of them will undergo SN1 and SN2. So it will not give you any racemic mixture, because only if it undergoes SN1 then it can give you a racemic mixture, and usually that is for tertiary halogenic alkane or tertiary alkyl halide. Then undergo SN1, you get a racemic mixture. Okay, let's look at so this is definitely wrong. Okay, look at the next one. Okay, this one is a carbonyl. So yeah, carbonyl, this carbon is trigonoplanar. So the Cn minus can attack either from the bottom or the top. Alright, so it looks like that. Okay, sorry. That's carbonyl. Okay, I hope you remember this. Okay, the Cn minus can attack from the top or the bottom, right? So either way, right? So you get a racemic mixture in the end. So 50-50, this is a chiral center. So definitely 2 is correct. Okay, for the last one, okay, so last one, HCl gas. Okay, the first step is this, is an electrophilic addition reaction. Okay, so how does the first step work? We add HCl, alright, HCl. So this part is delta plus, delta minus, electrons go to the H. So you get this compound. So I guess I can draw this one or just like that first. So the H goes to this carbon, and this carbon will become a carbocation, right? Carbocation over here. So the next step, what happens is the Cl minus that's produced can also attack from the top or the bottom. Alright, can attack from the top or the bottom. Okay, So I actually have to change this. This is CH3 and this CH3. Yeah. So this CH3 and then one of this is CH3. So if it does attack from the top and bottom, alright, you get because this carbon again, this carbon is carbocation is trigonal planar. Okay, trigonal planar. So the Cl minus can attack from top and bottom, and then you get a racemic mixture again, and you can see that this actually is your chiral center. Alright, so which means this is also correct. You get a racemic mixture. Alright, so 2 and 3. That's answer for 4. Okay, let's look at the next one. 5. Okay, let's see. Okay, let's look at question 5. Okay, which of the following can be observed with vanillin? Alright, so let's look at the functional groups here. Actually, this one here is an ether. Okay, this is what it looks like. Alright, so I hope some of you didn't get confused. It was actually an ether. Alright, okay, that's what it looks like. Alright, so you have a secondary alcohol, you have an aldehyde, and you have an ether. Alright, so warm acidified potassium dichromate turns green because it actually oxidizes the aldehyde. So this is correct. Let's look at the next one. 2,4-DNPH reacts to give orange PPT. Yes, it's right because there's aldehyde. Yellow PP form on warming. So I don't think so because you don't have either this structure. Okay, you don't have this structure or this structure. Alright, so that's for either form test. So which means the answer is only 1 and 2. Alright, okay, let's look at the next question. 6. Which of the following transfer will occur under given condition? Alright, so this one over here actually has the iodoform reaction. Okay, so I taught this in class. Alright, this is actually CH2I, but it doesn't always have to be CH3. It can be CH2I, it's also fine. Okay, this will give you a positive iodoform test. So this is actually correct. The second one, this is acid hydrolysis, but there's a problem. For acid hydrolysis, for CN to become COH, this has to be aqueous, right? So because it's gas, this one is wrong. Again, this is aqueous. Lithium monohydrate in dry ether is dry. You can't have water. So this is wrong. Yeah, this one doesn't really happen. It probably doesn't happen, yeah. Unless this is a benzene ring, maybe. Okay, but even there's a benzene ring, it undergoes tri-substitution. Right, there's phenol there. But anyway, it's not even phenol. Okay, so yeah, no reaction. So this is also 100% wrong also. Right, so answer is definitely A. Okay, let's look at the next question, 7. Okay, gem diols, right, which are hydroxyl groups, which is both OH hydroxyl groups bond to the same carbon, can spontaneously eliminate a molecule of water to produce a carbonyl compound. So which compound after complete hydrolysis gives a precipitate with this is actually toluenes, right? Okay, this is actually toluenes, Alright, so I think the precipitate here they're talking about is silver, right? This toluenes reagent, right? Okay, so so it must be an aldehyde basically. The catalyst must be aldehyde. So let's look at the first one. Okay, the first one you get 1,1-dibromobutane, which is this. 1,1-dibromobutane means you have a Br here and you have a Br here. So if you complete hydrolysis, okay, actually you take it as probably base hydrolysis, right? So if I add NaOH, take it as base hydrolysis, alright, and heat, okay, you end up getting a carbon with 2 OH here, right? Yeah. So that's what they're trying to say, alright? So this is called a gem diol, where both OH groups bonded to the same carbon, right? So the next step is it will occur spontaneously. You have to take away water. So I'm going to take away water from it. Okay, remove water. So once you remove water, okay, this is your product. 1, 2, 3, 4. So this is double bond O and a H. Okay, and this is actually an aldehyde. Right, this is an aldehyde. So it's actually positive with toluenes reagent. So the answer is A. Okay, I think if you 1 and 2 and 2 and 3 will not be the correct answer, because it is 1 and 2, you notice that the OH will be on different carbon. Okay, and this is not a gem. The OH must be on the same carbon atom. So if you did 2, if you tried C actually you end up getting this. 2,2-dibromo, you undergo base hydrolysis, you get OH here and the OH here. So actually when you remove water, means let's see, if you take away water, or take away the OH here and the H here. So you actually your product turns out to be a ketone. Okay, you're a ketone. So it's actually negative with tolons, right? So that's why it's also wrong. Okay, let's look at the next one, 8. Okay, beta carotene. Okay, beta carotene is responsible for the orange color. When a molecule, means one of this molecule, is oxidized by a hot concentrated acidified KMnO4, this is where oxidation will take place of the alkene. How many of these product molecules contain the ketone functional group? Okay, if you actually break over here, alright, in fact you get the ketone functional group. I'm just going to draw this part here. It will look like that. Okay, this is one of the ketone functional group. Alright. Oh, sorry, to go this way. Okay, so this CH3 is over here. So it's actually like this. Okay, but if you have any continuum, it becomes COOH. Okay, when you break the bond also. Alright. So this is a ketone functional group for both of them. Yeah. So this is 1. Okay, so what happens if you're going to break a lot more, right? So you're going to break here, 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 here. So it can be quite complicated. Okay. Okay, so I'm just going to show you very quickly. In fact, this one, this is actually 1. All right. This middle part will actually become a ketone. Okay, this part doesn't become a ketone. Okay, this part doesn't become ketone. What it becomes is this. Let me draw it out. It becomes this COH. Okay, I'm drawing this part here. Okay, I'm drawing this one here. When these two bonds break, what happens in here? So this one becomes C double bond OOH. And this is the special case. It's called ethane dioic acid. So this one is very unstable and can easily oxidize to carbon dioxide and water. Alright, so it doesn't give you any ketone. So this is out. Okay, this is out. This is out because they're all the same thing. Right, this one, forget it. Nope. Okay, so where are the other ketones? Okay, this part will give you the 3rd ketone. This one will give you the 4th ketone. This one will give you the 5th ketone. Right? And actually, yeah, this whole part, okay, after breaking this, okay, this part here will give you the 6th ketone. You see that? Alright, so actually the answer is actually B. The answer should be B. Okay, so take note. Okay, let's look at the next question, question 9. Alright, how many structural isomers with this molecule gives an orange PT with Brady's reagent? So this actually is your 2,4-DNPH. Okay, and a yellow PPT with alkyne aqueous iodine. So I guess it should have the methyl ketone. Right, it should have the methyl ketone structure. Right, so let's try to draw C5H10O. So I'm going to just draw the first one. Okay, 1, 2, 3, 1, 2, 3, 4, 5. Okay, so if you think about it, this is a CH2, this is a CH2, 10. So count 3, 6, 7, 8, 9, 10, 11, 12. 3, 6, 7, 8, 9, 10. Okay, 10. Just counting the hydrogen. Okay, 10 hydrogen. Good. Okay, so this is one possible structure. Okay, the other possible structure, you still must have this. So what you do is you play around with this. So this is actually, instead of drawing straight chain, you draw branching. So branching looks like that. So this should be a CH3 on the side. Okay? So that's why this is 1 and this is 2. Alright, so that's answer B. Okay, let's look at question 10. Okay, let's look at question 10. Alright. Okay, okay, let's look at question 10. Okay, which of the following shows the product formed when benzaldehyde undergoes a similar reaction with carbon monoxide in the presence of water? So this type of question, you probably have to try to come up with a pattern, right? So you can see that this is your structure, okay, plus carbon monoxide and water. All right. So what do you end up getting? You get C H2 and then become OH. All right, and this one becomes COOH, right? Okay, so hopefully you could see, I don't know, but maybe you can see that this was your carbon monoxide. Okay, water, the OH was here and the H was here. Can you see that? So that's how we look at it. All right. Okay, so let's see. So if I use a benzaldehyde, so let me draw benzaldehyde. Okay, just try to see a pattern here. Okay. Okay, let's try to see a pattern. So I try to draw benzaldehyde. This is what it looks like. Okay, so benzaldehyde plus the same thing, carbon monoxide plus H2O. So what you can do is, see whether you can draw it up. Just follow the pattern. I'm going to draw the benzene right here. Right, C H O H. Is that? So C double bond O H. 10. So I'm going to look at the answer. Okay, so I guess the answer is D. Right, a similar reaction with carbon monoxide and water. Alright, so that's how it's done. Let's look at question 11. Okay, okay, this was what I did in class. So it's the aldol condensation reaction. Okay, so in the present strong base, aldehydes can undergo addition reaction to form aldol compound. Alright, aldol is the hydroxy carbonyl compound. So they gave you an example. So if you remember the mechanism, right, so if you look at it carefully, let me see. You notice I mentioned that the hydrogen that is being removed is on the alpha carbon. So this, when I said this carbonyl, the carbon next to it is the alpha carbon, and that carbon, the hydrogen can be removed. So this is what happens. This is what you're going to get: C double bond O and a H. So C H2, can you see? All right, and this is a CH3. Sorry, so one H. So one hydrogen was from here was actually removed, right, and then it became a nucleophile. So it's going to react with the carbonyl, right, just to give you an idea of how it works. All right, so this lone pair will attack delta plus versus delta minus. It will attack this carbon, electrons goes to the O. So you get CH3, CH2, O minus at first. Alright, O more minus at first. So yeah, the H I will draw here. Okay, so this carbon, which is this carbon, right? It's this carbon over here. So there's a H, there's a CH3, and it's carbon. Alright. So after that, of course, we react with the water. Okay, the water came from when the H and the OH came out. We put when the H and the OH form water. So it will take the water from here. Alright, take the water from here. Okay, and then the O minus will combine the H and then you get OH. Okay? Okay, so very quickly we're going to do the same concept. So if you try it out yourself and you realize the answer is D. Okay, I'm just go straight to the answer. So why is the answer D? Okay, propanone will form CH2 minus. So you took away the H from this carbon, alpha carbon. So this is what you get. Alright, then with the carbonyl, CH3, CH2, CH2, C double bond O and a H. Alright, so just draw delta plus, delta minus. Okay, attack this carbon, electrons go to the O. So hopefully you can see that this is the answer. CH3, CH2, CH2, CH, O minus first, but later on it become OH with water. So this CH2, C double bond O, CH3. Okay, okay, so this is answer, right? B. Okay, so very important. So that's what they're testing. Okay, let's look at the next one. Okay, let's try this question. Question 12. All right. So what are the functional groups here? There's a ketone here. All right, a ketone here. In fact, this is an ester. This one actually is an ester. All right, it's an ester over here. This is a secondary alcohol, and this is a secondary alcohol. All right, and actually this is an aldehyde. Okay, this is aldehyde. Okay, so if I look at B and W for A, B, C, and D. Okay, let's look at for A, aldene and aqueous sodium hydroxide. Okay, it's positive for this this structure. It's also positive for this structure. So which means for V and W, alright, is A is positive for both, so it cannot be used to distinguish. Okay, 2,4-DMPH is also positive for your ketone and for your aldehyde, which means it's positive for both. You get orange PPT, so you can distinguish. Okay, this is very, very tricky, but I have to teach you something about hydrolysis of ester. It's actually, there's acid, alright, this question should say it's hot acid actually, alright. Anyway, okay, so if there's acid and there's heat, alright, what will happen is, the ester can actually undergo acid hydrolysis, right? The ester can actually undergo acid hydrolysis. So if you have not learned this, let me just run through very quickly. So if you have an ester like this, right, or esters, right, this. Okay, so this is your ester linkage. Okay, I'm gonna just highlight. Okay, so take note, this is your ester linkage. All right. So esters will undergo acid hydrolysis or base hydrolysis. So hydrolysis is probably like you add an acid hydrolysis, you add acid aqueous, alright, aqueous, and heat, alright, and heat, okay. So what really happens is this, what's actually really happening is this. So water, okay, water is over here, so hydrolysis must always involve water. So this is delta minus, and then delta plus. So the water will attack this carbon, alright, and electrons will go to this O, okay, and this bond will literally break. So you break the ester linkage. Okay, so what will be formed? You're going to get CH2 here, O, alright, but this bond will also break, okay, so the H will actually go to the O, you get OH, and then on the other side you get C double bond O, CH3, and OH, okay. So you always, when you hydrolyze an ester, you get a carboxylic acid and alcohol. It's like what are reagents when you form ester? You use carboxylic acid alcohol. When you hydrolyze it with acid, aqueous acid, you get carboxylic acid alcohol. And if you look at this structure here, this one turns out to be a primary alcohol. Alright? So this primary alcohol can be oxidized by the potassium dichromate, which means the orange will turn green. So there will be a positive reaction here. Okay, and if you look at for W, both are secondary alcohol, which means both can also be oxidized by potassium dichromate from ketone, and the dichromate will change from orange to green. So this should be correct. Okay, the answer for last one is actually, they put silver nitrate and aqueous ammonia, is actually Tollens. It's actually Tollens reagent. So Tollens reagent is only positive for aldehyde. So this is positive and it's negative for this. So the answer has to be D. Okay, so it's a bit tricky for question 12. Okay, let's look at the next one. Okay, which compound will not react with this? Okay, will not react with sodium boron hydride. Okay, so it's actually not carbonyl. Because sodium boron hydride will react with carbonyl. So it's not carbonyl, alright? But react with hydrogen. Okay, so not carbonyl, I take away option number 2 for now. Alright, so I take away this. Okay, so carboxylic acid, you remember carboxylic acid, it has to be reduced. It can only be reduced by lithium or aluminum hydride, alright, and become a primary alcohol. So this one is out. It will not be reduced by hydrogen. So hydrogen can actually reduce nitrile to CH2 and H2. Alright, nitrile becomes H2 and H2. Hydrogen, of course, can react with alkene to form alkane. So the answer is 3 and 4. Alright, okay, let's look at the next one. Cyanohydrins are useful intermediates. Okay, so they can be made by reacting carbonyl with hydrogen cyanide. Okay, so let's see this one. So propanone looks like this. Alright, this is propanone. Alright, so react with HCN. Yes, the Cn minus can attack from the top and the bottom of this carbon because it's trigonal planar. Right, Cn minus can attack from the top or the bottom from both directions. So, but you look at the product at the end of the product. At the end of it, you look at your product over here. Okay, this is of course your final product. Just going through the final product. So this is your final product, but the problem is this is not a chiral carbon, so you will not get a racemic mixture. So it's wrong. Okay, propanol reacts with HCN at a faster rate. So yeah, because aldehydes has less steric hindrance, so it's easier to react. Okay, because this one is a H, right, compared to propanone, whereby both sides are carbon, right? So which means less steric hindrance, the nucleophile can attack, right, the carbon more easily, can attack this carbon more easily. Yeah, okay, less steric hindrance. So that's correct. Cyanohydrin obtained from the reaction can be distinguished from propanone by warming with sodium hydroxide. Okay, so let me see. Okay, so they say can be distinguished from propanone. Okay, so what they're trying to say is this. So you have sorry. Okay, let's try it. So you have propanone and you have the cyanohydrin. Okay, this is the cyanohydrin. So they can be distinguished from by warming with sodium hydroxide. So sodium hydroxide actually can react with this one here, alright, nitrile. So you warm it with sodium hydroxide, the Cn will become COO minus Na plus. So now actually because of that, it's actually going to be soluble in the solution. Alright, so because it's soluble, you only see one layer. But for propanone, if it's not so soluble, you probably will not have any reaction and maybe you might just see two immiscible layers. Alright, so this one there's a reaction with nitrile and there's no reaction with propanone when you warm with sodium hydroxide. So this one, I guess they take it as you can actually distinguish them. Alright, so the answer for question 14, the answer for question 14 is actually C. Alright. Okay, so let's look at the next question. Alright, let's look at question 15. Okay, which of the reaction does a carbon change from sp3 in the intermediate to sp2 in the product? So the answer is actually B. Alright, let's see why the answer is B. I'm not going to go through the rest, but let's see what the answer is B. So this is your intermediate. Okay, this is probably your intermediate if you understand the mechanism well. Okay, so this is actually your carbon here, which is sp3. Alright. So finally, this is your product. Okay, finally, this is your product. The product, of course, is this. Alright, this is your product. Okay, and back to this carbon now is actually sp2. Right? So yeah, so that's why answer is B. So let's look at the next one. Retake reaction is a popular method to synthesize alkene from ketones. Okay, essentially you just have to see a pattern here. Okay, you see a pattern here. Alright. So this H here, okay, this H here is H minus. Alright, so it managed to actually extract a hydrogen from here, right? It managed to extract a hydrogen from this CH3. So the H minus, pull out H plus, actually I would put maybe there to be hydrogen that's being produced. So this become a minus, alright? This become a minus, okay? So maybe you just don't have to go in detail mechanism, alright? But this is roughly how it works. Delta minus, delta plus, and this lone pair will attack this carbon. Okay, you probably have to break this bond, so this becomes CH2. Can you see that? Alright, and eventually the O of course get removed. So you're gonna follow exactly the same concept and see how you draw this. So the diagram shows a reaction sequence. Which of the following will give an observation with O? Okay, so with this, I hope you get N. Alright, so what is N? Okay, what is N? How am I drawing the product? So I can see that I'm gonna add this guy. I'm going to take out a H from this carbon. Okay, I'm going to take out the H from this carbon, and this group will replace my O. Okay, so I'm going to have to take away this O and replace it with this part here, but without the H. So N, I'll draw N now. N should look like CH3, CH double bond. Okay, this will be CH, CH3. Is that? So this is my N. So after that, you add H plus and steam. So H plus and steam, which is actually, you can take it as this is your concentrated H3PO4. Alright, and then in water, steam. So high temperature, high pressure, what they're trying to show you is going to form an alcohol. So what is O? O is this. So this is O. So this one will react with water, right? Okay, so that becomes alcohol. So this is how I'm going to draw it. OH. Okay, and H. Okay, so this is a final product. Okay, so does it react with aqueous alkaline iodine? Yes, it sure does. It has this structure here. Alright, PCl5, yes, it sure does because it has the alcohol group. Yeah, so this is fine. 2,4-DNPH, no, because there's no carbonyl anymore. Alright, so the answer is the 1 and 2 only. So I guess this answer would be B. Okay, let's look at the next one. 17. Okay, which compound can be formed by addition of B2 to another molecule in the presence of platinum catalyst? So this is like hydrogen, right? This is it's an isotope of hydrogen. Okay. This one here. This one should be actually this one should be just be G21. Okay, it should look like that. Alright. Okay, so which one? So if you look at this, what was before this? Means what was before this? Okay, hopefully you can tell it was actually before this was CH3CN. Alright, so CN undergoes hydrogenation, alright, with the presence of a platinum catalyst, D2, D2. Okay, platinum catalyst, it will be fine. Alright. Okay, how about this one? I've never learned this one. There's no, I think you're supposed to kick out a H and replace with a D. I don't think we've learned this before. So I'm just going to put a cross here. So this one here, if you work backwards, hopefully you can see that this is a D, this is a OD, right? So in fact, it was originally ketone. So ketone can be reduced, alright, to a secondary alcohol. So sorry, this is a secondary alcohol. Yes, that's right. So this actually is a secondary alcohol. Okay, right. So imagine your D as a H. You can see that, and this carbon actually has two alkyl groups, two alkyl groups. So this is a secondary alcohol. Right. Okay. So this is possible. All right, this is possible. So 1 and 3. Okay. So 17 is C. So let's look at the last few questions. Right. Okay, let's try question 18. All right. This is your aldehyde. Yeah. CH3, CH2, C double bond O and H. Right. So they say the intermediate form in this reaction is planar. So the first part is actually the CN minus, right? It's a nucleophile. You take this carbon, right? So you're going to draw this first. All right. Then the second step, of course, you add your HCN, right? So the O minus will take this H. Let's transfer to carbon. Okay, this is the overall reaction. So if I have the aldehyde plus HCN, you get CH3, CH2, COH, H, and CN. Okay, the intermediate product formed in this reaction is planar. Definitely not. This carbon is already this intermediate. This carbon is already tetrahedral, so this is definitely wrong. Only one product is obtained since this is an electrophilic addition reaction, but this reaction is not electrophilic addition, it's nucleophilic. This is a nucleophile, right? It's carbonyl, right? Yep. Okay, so carbonyl undergoes nucleophilic addition. So the uncatalyzed reaction between propanone and HCl occurs faster than propanol. Okay, this is a ketone and this is an aldehyde. So in fact, aldehyde is always faster because it's less steric hindrance. Less steric hindrance. I think you know that. Alright, because this carbon here has one H here. So this H is not a bulky group. It less steric hindrance and Cn minus can attack more easily. So which means this is also wrong. Alright. The same product can be obtained by heating 1-chloropropan-1-ol with ethanolic NaCN. So let's draw 1-chloropropan-1-ol. So this is how it looks like. Okay, so I have to take away this. So I'm just gonna put in a Cl here and an OH here, right? Okay, in fact we did a few of such questions already. They say which is correct. Okay, the same product can be obtained by heating. So this one with ethanolic NaCN. This is a nucleophilic substitution reaction. The Cl will be substituted. So this is what you get. So the Cl will become Cn, right? Which is actually the same, right? So the answer is actually D. Okay, let's look at question 19. All right, you can see what the functional groups always have to label the function. This is the aldehyde. Okay, this is a bromoalkane alkyl halide, and this is an alcohol. Okay, this is alcohol. Right? Okay, so let's look at what the options. But I'm just going to maybe go straight into the answer. Right. So the answer is actually C. Okay. So the first step is actually Tollens reagent, right? Tollens reagent. So Tollens reagent is actually an oxidation reaction. Okay, it's actually an oxidation reaction. So this aldehyde will be oxidized first. So I'm just going to draw the first part, right? So after step 1, this is what you have. COO minus. Alright, and then of course your silver mirror. And then they add hot alcoholic sodium hydroxide. Okay, so this mechanism here should be elimination. Okay, elimination for halogenate alkane. So with after step 2, I'm just going to take away the Br and the H from here. So I'm going to get this. Okay, so this will end up becoming a double bond, and this will be like that. Or like that. Okay. So heat in the presence of concentrated H2SO4. So with the presence of concentrated H2SO4, because it's acid, this CO minus becomes COH, and then it will react with the alcohol. So you can take away water. Okay. So once you take away water, this is what you get. So C double bond O. This C will join to this O. Can you see that? And this O will join to this carbon, and this carbon will form another bond here. Alright, I think my drawing is not so good, so yeah, just place this part, need more space. Okay, this oxygen is joined to one more carbon. Alright, carbon here, and this carbon is joined to another carbon, which is this one, and this carbon is the one with a double bond, and then it joins to this one. Can you see that? So that's why this is the answer. Okay, that's why this is the answer. Alright, okay, so that's C. Okay, let's look at the next one. Okay, let's look at the next question. Last question. Okay, diols formed on the same carbon are generally unstable and will undergo the following reaction. So this is a jam diol question that we went through just now. So it seems to be quite popular. Okay, OH, OH. So what they're doing is you're going to remove water. Okay, take away water. So this is what you get. Alright, C double bond O. Alright, plus water. Okay, it's very unstable, so you always remove water immediately. Okay, so compound W and B and W are both reacted hot equals sodium hydroxide followed by dilute acid. So if you notice over here, there's Br. So let's try for compound B. Yeah? So if you add sodium hydroxide, firstly this will become OH. Alright. This one cannot remove, yeah, because partial double bond character. Okay, this one here I'm gonna try to draw it immediately. So it becomes OH and OH here, right? So it's going to take away water, so I'm going to take away water. Right, can you see that? So take away water. So if I take away water, right, this becomes a C double bond O. Maybe draw again. So this becomes a ketone. Okay, so this is a product. Okay, ketone and alcohol over here. Okay, for the second one, if you add hot potassium hydroxide, okay, you get CO minus, but later on you add dilute acid, so we come back to COH. Okay, so let's look at this one here. CH2, alright, C, Br, okay, but Br will become OH, right? So I'm just gonna take away. So the Br will become OH, okay, OH and OH. Okay, because there are two Br there. So again, you're going to take away water, right? Take away water. So your end product is going to be an aldehyde. Right, so you take away, and your end product is an aldehyde. So that's what they want you to be able to tell. So you've got ketone and you have aldehyde. So you're going to tell the difference. So can distinguish? No. Both will give you orange PPT with ketone aldehyde. Feelings, yes, alright. Feelings, okay, because feelings is positive for aldehyde, aliphatic aldehyde, which it is, alright. Okay, and this carbonate, good. Carbonate can because it's a carboxylic acid here, but there's no carboxylic acid in the product of V. So hot dichromate. Okay, dichromate can oxidize. Let me see. Oh, dichromate can oxidize the alcohol and also can oxidize the aldehyde. So this is not a good one. Aldene and aqueous. So there's either form test. Let me check. Okay, so there's only an either form reaction over here. Okay, but not for anyone for the product of W. So this is actually fine. Okay, so the answer is 2, 3, and 5. 2, 3, and 5. Right, so that's how it's done. Okay, so that's it.
Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.